Every 22 minutes, Earth is hit by a massive, invisible blast of radio waves. It arrives with mathematical precision from the Scutum constellation. Astronomers have tracked the source to a location they call J183910, an object buried in a crowded star field 15,000 light-years away. But the signal isn't new. When researchers dug through old archives of data from radio telescope arrays, they realized this pulse has been hitting our planet continuously since 1988. The problem is that when you compare this 22-minute signal to every known celestial object, the computer returns a clear match not found. It doesn't align with our existing models for how a star should behave. While a signal this consistent often sparks talk of an alien origin, the energy levels required point toward a natural, albeit unknown, cosmic phenomenon. Because a 22-minute natural radio burst shouldn't be possible according to current theory, we have to re-examine the physics of dead stars from the ground up. The most likely candidate is the pulsar. These are the super-dense, rapidly spinning cores left behind after a massive star collapses. Inside a pulsar, charged particles accelerate along intense magnetic field lines, broadcasting beams of radio waves. Because the magnetic poles aren't aligned with the star's rotation, these beams sweep across space as it spins, looking like a blinking lighthouse from Earth. This chart tracks pulsar health. The death line marks where a pulsar is too slow to emit radio waves. Normal pulsars spin rapidly, staying in the active region. Rotating every 22 minutes, J1839-10 sits deep in inactive territory, past the threshold for radio emissions. According to our current understanding of pulsar physics, an object spinning this slowly should be completely silent. Another possibility is the magnetar. These are neutron stars with magnetic fields 1,000 times stronger than a typical pulsar, which could theoretically allow for longer pulse intervals. However, magnetars are incredibly energetic. Their activity is always accompanied by intense bursts of X-rays alongside their radio output. When we pointed our X-ray telescopes at J1839-10, we saw nothing. The source emits clean radio waves with no X-ray signature at all. By ruling out standard pulsars and magnetars, we are left with a star that defies our established classifications. This has led researchers to a more specialized theory, the white dwarf pulsar. For a white dwarf to behave this way, it must be massive, at least 80% of the mass of our Sun, to generate a magnetic field strong enough to pulse. Unlike neutron stars, these objects are driven by electrons. This difference in internal mechanics allows for a much slower pulsing cycle. Theoretical white dwarf pulsars are expected to pulse every 100 to 1,000 seconds. At 1,320 seconds, J1839-10 is the closest physical match to this hypothetical class of stars. J1839-10 isn't the only anomaly recently discovered. The scary Barbie supernova is currently emitting 100 times more energy than any typical supernova, lasting for years instead of weeks. These discoveries are revealing the limits of our current astronomical categories. We are finding objects that don't fit into the boxes we've built for them. These match not found errors represent the most exciting frontier in science. They prove that there are powerful, unknown classes of stars in the deep dark of space that we are only just beginning to name.